Micronutrients. Vitamins are organic substances that the body needs for its metabolism but cannot manufacture in sufficient quantity, and trace elements are essential components of the diet that are needed in small amounts. Individual micronutrient deficiency causes typical symptoms and signs depending on the vitamin or element involved. Importance of micronutrients. Energy production. Many micronutrients help the body convert food into energy, like B vitamins. Immune support. Some vitamins like vitamin C and D and minerals like zinc help in boosting the immune system. Bone health, calcium, vitamin D and magnesium are crucial for maintaining strong bones and preventing conditions like osteoporosis. Blood health, iron, folate and vitamin B12 are involved in the production of red blood cells and preventing anemia. Antioxidant functions. Some micronutrients such as vitamins A, C and E protect cells from damage caused by free radicals, contributing to aging and disease prevention. Vitamins are classified into fat-soluble vitamins and water-soluble vitamins. Water-soluble, these include vitamin C and the B vitamins like B12, B6, folate, and riboflavin. They dissolve in water and are generally not stored in the body, so they need to be replenished regularly through diet. Fat-soluble. These include vitamins A, D, E, and K. They are absorbed with dietary fat and stored in the liver and fat tissues for later use. Vitamin A is found in several forms that can be classified into preformed vitamin A, also known as retinol, and carotenoids. Now, vitamin A is most known for the role it plays in sight, so a deficit of this is usually related to night blindness, which is also called nyctalopia. Vitamin D is another extremely important fat-soluble vitamin. Its active form is 1.25-dihydroxycholecalciferol, which is involved in the absorption of calcium and phosphorus in the intestine, and its use in bone formation. Deficiency causes rickets in children and osteomalacia in adults. Vitamin E encompasses 8 very similar compounds, 4 tocopherols and 4 tocotrienols, with alpha-tocopherol being the most active. Vitamin E is an antioxidant that acts in conjunction with vitamin C to prevent peroxidation of unsaturated fatty acids from cell membranes by oxygen radicals. Vitamin K. The two natural forms of vitamin K are phylloquinone, also known as vitamin K1, and menaquinone or vitamin K2. Vitamin K is required for post-transcriptional carboxylation of glutamic acid residues in proteins to form G-carboxyglutamic acid, often referred to as GLA. These modifications made by vitamin K occur, among others, in proteins involved in blood clotting. Hydrosoluble vitamins. Hydrosoluble or water-soluble vitamins are polar compounds that, with the exception of vitamin B12, tend to be rapidly absorbed into the upper part of the small intestine, which is the duodenum, mainly through an active sodium-dependent transporter or by diffusion mediated by a transporter. Thiamine. The physiologically active form of thiamine is thiamine pyrophosphate. Among the enzymes in which it acts as a cofactor are pyruvate dehydrogenase, also known as acetylpyruvate-CoA, 2-oxoglutarate dehydrogenase, or 2-oxoglutarate succinyl-CoA, and transcatolase. Therefore, it is involved in the metabolism of carbohydrates, lipids, and amino acids. Given that it is present in nerve and muscle cells, activating ionic membrane channels, it can also act without being a cofactor. Its deficit causes Beriberi and Wernicke-Korsakoff syndrome. Riboflavin. Riboflavin is a constituent of FMN and FAD coenzymes that act as electron acceptors in the electronic transport chain, so it is involved in ATP production. Riboflavin deficiency is rare in countries where regular milk intake is part of the diet. Niacin. Niacin is the term used to describe nicotinic acid and niacinamide. Niacin is part of NAD+ dinucleotides, present in the transfer of electrons in the electronic transport chain, and NADP+, a reducing agent of a large number of biosynthetic processes, involved in a large number of redox reactions. Niacin can be synthesized from tryptophan. 60 mg of tryptophan generates 1 mg of niacin. Niacin deficiency causes pellagra. Vitamin B6. The three natural forms of vitamin B6, pyridoxal, pyridoxine, and pyridoxamine, as well as its 5' phosphate derivatives that are all interchangeable amongst themselves and have vitamin B6 activity. Pyridoxal phosphate is a cofactor with over 60 enzymes that catalyze amino acid reactions. Vitamin B6 deficiency produces neurological symptoms, as well as dermatitis and glossitis. Vitamin B12 is considered a generic term for a group of cobalt-containing compounds known as coronoids that can be converted into methyl and adenosylcobalamin, the two main coenzymes of cobalamin. Methylcobalamin is a coenzyme of methionine lysine, also referred to as homocysteine methionine, that acts in conjunction with methyl tetrafolate. Adenosylcobalamin is a coenzyme of methylmalonyl-CoA mutase, which is also known as L-methylmalonyl-CoA succinyl-CoA. A deficiency in vitamin B12 results in pernicious anemia and neurological symptoms derived from spinal cord demyelination. Vitamin C. Vitamin C includes L-ascorbic acid and its oxidized derivative L-dehydroascorbic acid. Vitamin C is a water-soluble antioxidant that facilitates various hydroxylation reactions. As already mentioned above, it acts in conjunction with vitamin E to prevent peroxidation of unsaturated fatty acids from cell membranes. A deficiency in vitamin C causes scurvy, which affects proline hydroxylation and results in defects in the tertiary structure of collagen. Folate. Folates are a group of compounds derived from tauroyl glutamic acid. In the body, it is mainly found as tetrahydrofolate, also known as THF, 5-methyl tetrahydrofolate, and 10,4-methyl tetrahydrofolate. Folates are characterized by their ability to donate and accept carbon units, as well as playing an important role in cell proliferation. Folate is a vitamin that works in conjunction with vitamins B6 and B12. A deficiency in folic acid is also known as macrocytic and megaloblastic anemia. Biotin. Biotin is an essential growth factor in many organisms that are widely distributed in food, so its deficiency in humans is rare. Biotin acts as a coenzyme in carboxylation reactions, behaving like a CO2 transporter. Biotin is important in gluconeogenesis and lipogenesis and also plays a role in the catabolism of the lateral chains of amino acids. Its deficiency has been noted in patients with parenteral nutrition lacking in biotin and patients who consume large amounts of raw eggs. Such patients have skin and neurological symptoms. Pantothenic acid. Pantothenic acid is a component of coenzyme A, therefore it is involved in many of the main metabolic pathways. In cases of extreme malnutrition, there are non-specific symptoms such as headache, tiredness, as well as a burning sensation in the foot. Trace elements. Trace elements are defined as minerals that are necessary for the body in small amounts, that is, less than 100 milligrams per day. However, some of them may be classified as ultra-trace, which means less than 1 milligram per day. Cobalt. there is little evidence that cobalt plays a role in human nutrition beyond being a component of vitamin B12. The microflora of the human gut is not capable of using cobalt to synthesize physiologically active cobalamin. Copper. The need for copper is partly due to its role as an enzyme cofactor. 80 to 90% of the copper in circulation is found in ceruloplasmin, responsible for oxidizing Fe2+ to Fe3+. Copper deficiency is rare, but when it occurs it results in neutropenia, microcytic anemia, and mental impairment. Iron. Approximately 65% of the iron present in the body is found in the circulatory system as part of hemoglobin. The clearest effect of iron deficiency is the reduction of the oxidative capacity of the muscle that leads to a decrease in work performance efficiency. Iron deficiency is associated with microcytic anemia. Magnesium. Magnesium is present in more than 300 enzymes in the body, particularly those involved in energy metabolism, as well as DNA replication and RNA synthesis. Its deficit causes muscle spasms known as tetany, paresthesias, and seizures. Magnesium is also involved in the release of the parathyroid hormone, so hypomagnesemia can cause hypocalcemia. Manganese. Manganese, like other trace elements, can act as an enzyme activator or as part of metalloenzymes, so its deficiency could affect the metabolism of carbohydrates, glycosaminoglycans, and cholesterol. Molybdenum. The role of molybdenum focuses on the redox function of the element and its need as a cofactor in the form of molybdopterin in 4 enzymes: oxidase sulfite, aldehyde oxidase, xanthine dehydrogenase oxidase, and amidoxime reductase. Selenium. Due to its chemistry, it can replace sulfur atoms in methionine and cysteine. Selenocysteine encoded in the genetic code is found in proteins such as glutathione peroxidase and 5'-deodeinase. Selenium and vitamin E deficiency causes skeletal muscle and heart degeneration, causing muscular dystrophy, also known as Cachon disease. Iodine. The only role iodine has in human metabolism is as a component of thyroid hormones. These play a very important role in the metabolism of the human body. The absence of iodine during the development of the fetus can cause cretinism. Zinc. Zinc is a cofactor of over 100 different enzymes of all metabolic pathways, such as superoxide dismutase, alkaline phosphatase, polymerase DNA and RNA, and carbonic anhydrase. With such a wide distribution, it is not surprising that zinc deficiency results in a high number of disorders. Zinc deficiency is associated with stunted growth, slowed healing, alopecia, and nasolabial dermatitis.